What is up, chemistry people? Who is ready to write some net-ionic equations? Alright, as you take a look at your notes, you're given a couple of reactants, told that a precipitation, aka double replacement reaction, is going to occur. We want to write the balanced chemical equation, and then come up with identifying the precipitate, and from there, write the overall net-ionic equation. Lots of nomenclature, it's never going away. Alright, so let's start off with mercury 2 chloride. Mercury got that funny symbol Hg, it's aqueous. We add to that a solution of aqueous potassium sulfide. Alright, now that we've got our formulas from the names for our reactants, let's think about the products that can form. Remember, in a double replacement reaction, the cation from one of your aqueous compounds hooks up with the anion from the other. So we would form mercury 2 sulfide and potassium chloride. Now, the first thing I want to do is figure out which of these things is going to form the precipitate or the solid. Notice that I've left some parentheses here for me to think about my decision. Lucky for us, to help us make that decision, we've got a handy list of solubility rules. As I look at the two compounds that formed, and I look at my list of solubility rules, I'm going to focus on the anions for the most part to help me determine which of those compounds is going to be soluble or form the insoluble solid precipitate. As I look at mercury sulfide, the anion here, sulfide, is in the insoluble compounds list. Now there are some exceptions, however, mercury 2 is not one of them, which means that my mercury 2 sulfide is going to be the solid precipitate that forms. To double check, I'm going to go to my other compound, potassium chloride. Chlorides are typically very soluble compounds. There are some exceptions, for example, when it's with silver, lead, or mercury 1. So here we're going to have, again, another aqueous solution. Okay, the next thing I want to do is balance my chemical equation. To do that, I simply need to add a coefficient of 2 in front of potassium chloride. Now, I want to come up with the overall net-ionic equation. The very first thing I'm going to do is write the complete or total ionic equation, where all aqueous compounds are split apart into their ions, all solid precipitates are kept together. So as I think about this, an aqueous solution of mercury 2 chloride is really going to consist of aqueous mercury 2 ions and aqueous chloride ions. Notice that my ratio here is 1 to 2 based on the ratio in the original formula for mercury 2 chloride. An aqueous solution of potassium sulfide is really going to consist of aqueous potassium ions and aqueous sulfide ions. Again, the ratios that I'm using here are based off of the ratios in the original formula. Mercury 2 sulfide is not going to exist as ions, but as a solid unit. And so I'm not going to split that apart. My potassium chloride here is going to exist as potassium ions and chloride ions. Again, in this last one, even though the ratio of ions in the compound is 1 to 1, I do have to distribute this coefficient of 2. It helps us follow the law of conservation of mass. Alright, now as I try to write my net ionic equation from my complete or total ionic equation, I simply have to eliminate all of the spectators. Spectators, remember, are going to be in the same phase on both the reactant and product side. They haven't really undergone any sort of chemical change. Notice that my chloride ions and potassium ions fit that definition. So my final net ionic equation is simply going to illustrate or highlight the reaction between aqueous mercury ions and aqueous sulfide ions to form the solid precipitate mercury 2 sulfide. This is my final net ionic equation. Now, once you get the hang of this, you may not have to write out the complete total ionic equation. You can simply look at your precipitate that forms and pull the ions out from the reactant side to help you write your net ionic equation a little faster. And we're done.